we are going to discuss about the reflection and refraction based on the wave theory of light. Let us take first of all the explanation of refraction by means of the wave theory of light. Okay, let us choose XY as the interface between two media. PQ is the incident ray. This is the normal to the plane of incidence. So angle of incidence is I. Let me draw the incident wavefront by means of another color. So this is at this point is the wavefront strikes at this point and t is equal to 0. Since incident wavefront is normal to the incident ray, I am considering this, which means this angle is 90 minus I, and this angle comes out to be I, right? Now at what time? So at t equal to 0, this is the location of this wavefront, right? So this is the location, so this is the point. So if I say QR, this is the time at t equal to 0. So this point, at what time this point will strike this point? This point of view. If I say this is yes, at what time R will reach to the point yes? At what time R will reach the point yes? I will say that it is equal to tau. In that situation, what will be the distance R? The point R strikes the point yes at time t is equal to tau. The point R is striking the point S at time t equals to tau. In that situation, I will say this is equal to V1 tau. R strikes the point at t is equal to tau. So I can say this distance is equal to V1 tau, where V1 is the speed of light in this medium. Right, so now R reaches to this. So what I am saying is that it is initially here, it will come. The wavefront is traveling likewise. It reaches here, right? It reaches likewise only. So it is traveling. So initially this wavefront is here. Now so the wavefront is here at t equal to 0. Then this point is now touching the surface. After some time this will touch, 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 this will touch. Ultimately this point reaches here. So this is what you understand. So this is a very important point you have to understand. So this is what I am getting. Now looking at the triangle QRs. Looking at the triangle QRs, tell me what is sin I is equal to. Sin I. Looking at the triangle QRs, sin I is equal to opposite side whose length is V1 tau divided by QS. V1 is the speed of light in this medium. Let the refractive index of this medium be N1. Now the light which are incident here at t is equal to tau undergoes refraction. Now let me take this angle as R. Drawing the refracted wavefront now. So that means I have to draw the wavefront in such a way that they are perpendicular, right? So what I will say, this is the wavefront at t is equal to tau. T is equal to tau, this is the wavelength. Here the velocity is v2. Now let me take this point as M. This angle is R. This angle is 90 degree. This total angle also is 90 degree. That doesn't matter. So this angle is R. What will be this angle? 90 minus R. Correspondingly, this angle is R itself. Right. That angle is R itself. So I can say sin R is equal to, and one more thing you can say here is Q. What will be the length Q? So this is a t equal to 0, this is a t is equal to tau. So from t equal to 0, so by the time time this moves from here to here, this also moves from here to here, right? By the time this moves from here to here, this moves from here to here as well. So I can say Qm is equal to speed of light in that medium, which is v2, and the time interval. Here it is t equal to 0, here it is t is equal to tau, so v2 into tau, right? By the time this reaches here, so this is reaching here, as it moves likewise, the wavefront, the refracted wavefront starts moving likewise, right? So this is how I am drawing. So Qm is equal to v to tau, so I can say sin r is equal to Qm divided by Qs, which is equal to v2 tau divided by Qs. Now we will divide this equation. Sin I divided by sin r is equal to v1 divided by v2, that is what is called the n2 divided by n1, right? And that is n2, 1. The refractive of this medium is n1, the refractive of this medium is n2, so v1 by v2 we have learned in the chapter optics as n2 by n1, so this is n2, 1. And we know that this is the famous equation. This equation is Snell's law. This is the famous Snell's law, and this is how we can use wave optics to explain reflection. Refraction. Now we will draw it in the same figure. How can we explain a reflection based on this theory? Okay, so I'm going next time we will consider the theory of reflection. So only small changes required. Now that much is done here. Correspondingly in reflection, the wave travels back to the same medium, right? That means what I'm going to do here, I'm going to consider radius. Now the reflected ray, so I will say the angle of reflection is equal to R. The angle of reflection is equal to R, angle of incidence is I. Now drawing a perpendicular, which is nothing but the reflected wavefront, right? Drawing a perpendicular. Okay, yes, the reflected wavefront I am drawing. How it is clear? Now I can say this angle is R. This one comes out to be 90 minus R, so obviously this angle must be R. Now drawing the reflected ray here, reflected ray. This is the reflected ray. Now what I can say here is, okay, wiping out this 90 minus I. Wiping out this also. Okay, right, no, that is required. V1 from. Now PQ R S T. Now so from here I can say Qt is equal to, so this is the t, this is the wavefront at t equal to 0, this is the wavefront at t equal to tau, right? So this time is t is equal to tau, this time is t equal to tau, this time is t equal to 0, so my question, what will be this distance again? V1 tau. Why V1 tau? Because the speed is V1 here. So from here what I am doing is Qt is equal to V1 tau. Okay, now we will take it once again. What is sin I? Sin I. Sin I is equal to sin I. Taking the triangle QRS. Taking the triangle QRS, what is sin I? Okay, now to avoid that condition, I am wiping out these things. What is sin I? Looking at the triangle QRS, I think I will get as V1 tau divided by QS, right? Similarly, what is sin R? What is sin R? Look at the triangle QTS. Take the triangle QTS. What is sin R? Sin R is QT divided by QS. V1 tau divided by QS again, right? I got sin I is equal to V1 tau by QS. I got sin r is also equal to v1 tau by 2s, which implies I is equal to r. That is the explanation of reflection on the basis of the wave theory. So in the next discussion, we will study about Doppler effect in light, non-relativistic Doppler effect in light. So we are not considering relativistic effect. We consider non-relativistic condition. According to our knowledge in first year, we have studied that Doppler, in the case of Doppler effect, the apparent frequency is equal to actual frequency to C minus V observer divided by C minus Vs. We have to keep the vector symbols in order. This is the formula for Doppler effect we are studying in first year. I am going to take the same formula for the second year also. For a stationary observer on Earth. For a stationary observer on Earth. What do we say? For a stationary observer on Earth, the apparent frequency f is equal to f0 into c divided by c minus vs with the proper vector symbol. Now it implies what is the changing frequency delta f is equal to? It is f minus f0, which I can say here f minus f0, which is c minus vs minus c, the whole divided by c minus vs. Okay, sorry, what more thing I am going to do? So it is f minus f0 into c divided by c minus vs minus f0. Okay, otherwise I would have made mistake. Which is, so from here I can take f0 common factor, then c by c minus vs minus 1, right? With proper vector symbol. Here also I put the vector symbol. Always speed of light is considered to be positive. So f0 into, now we will simplify this expression. C minus, taking LCM, C plus Vs divided by C minus Vs, right? Now what can we say here? F0 into C, so C minus C is 1. So in this case I will get delta F is equal to F0 into C divided by, sorry not C, C will be cancelled, Vs divided by C minus Vs. So apparent frequency is equal to actual frequency into Vs divided by C minus Vs. This is the expression for the changing frequency, not apparent frequency. The expression for changing frequency is f0 into Vs divided by C minus Vs. Already. Now let us take the case of this one. Now we are concentrating on our formula, case 1. Star. This is generally observed with stars. Star, or simply I will write source. Source moving towards Earth. Source is moving towards Earth. The source of light is moving towards Earth. That means this is where the surface of Earth is located. This is where the source. Always light is moving in this direction. Now the source is also moving in the same direction. So in this case I will say Vs is equal to plus V, because those velocities in the direction of light will take positive. That's a sign convention. Those velocities in the direction of light are taking positive. So in that case what will be delta F is equal to F0 into C divided, sorry not C, V divided by, substituting Vs as plus V, V divided by C minus V. Now C minus B is positive, so in this case it is greater than 0. Which means F delta F is according to our knowledge F minus F0, which is greater than 0 implies the observed frequency is greater than actual frequency. The frequency that we are observing is greater than actual frequency. So that will lead to what is called red-blue shift. That will lead to what is called blue shift. It is called blue shift. This will result in blue shift because the frequency in the electromagnetic spectrum, the frequency of blue is greater than the frequency of red. So this is blue shift. Now the second case, source moving away from Earth. Source moving away from Earth. In that case, delta F is equal to F0 into. So what I take here in this case, ds is equal to minus v, right? It's moving away means the direction should be upwards or opposite one. So in this case, it will be minus v divided by c plus v. And I will say it is less than 0. What does that mean? F is less than F0. In that case, F is less than F0. This will result in what is called a red shift. This will result in a red shift. This will result in what is called a red shift. I hope this much is absolutely clear to you.